Hello students, welcome to Young Cubs. We are continuing the chapter of properties of materials, and today is the fifth session and the last session for this chapter. Yesterday children, we had spoken about ionic bonds and covalent bonds. Let's take a quick recap of the differentiation between covalent bond and ionic bonds. Okay, now species involved, they say there are atoms out here. Atoms are involved, that is, neutral particles are involved. Over here, the neutral particles become ions by acquiring a charge. If a positive charge, we have a cation. If they have a negative charge, it is an anion. So a cation and an anion bond together and form a covalent, form an ionic bond. Coming next to the electrons, in covalent bonds, electrons are shared, whereas in ionic bonds, they taken by more electronegative participants. So basically, charges are exchanged. Okay, negative charges are exchanged, or rather, it's been given and taken. Interactions, balance of attractive and repulsive forces between ions. So they have a bonding, they have forces of attraction between them, and due to which they bond together. Whereas here in ionic bonding, there are weak electrostatic forces which keep the ions bonded together, and hence they break easily and bond with something else. Examples of covalent bonds are water, chlorine, oxygen, nitrogen. Okay, whereas examples of ionic bonds can be sodium chloride, calcium carbonate, magnesium oxide, many of those kinds. Okay, where metal bonds with a non-metal. Children, there's one aspect which I have not tapped properly on, is about valency. How does when forming a chemical compound, how do valencies work? Coming to the same examples that we had done yesterday, looking at NaCl. Okay, NaCl. Okay, Na is sodium, which has a valency of 1. How a valency of 1, children? It is ready to give away 1 electron of its outermost shell. Okay, chlorine also has a valency of 1. Why? Because it has 7 electrons in its outermost shell. It wants 1, and that's the reason why it's ready to accept 1. Remember the definition of valency: an atom where the atom is willing to accept, donate, or share electrons. So in chlorine, it is willing to accept 1. It is difficult for it to give out 7. Rather, accept 1 and attain stability. So valency of chlorine is also 1. If we do the crisscross method like we did in aluminium oxide, okay, it is N1C1. 1, if the valency is 1, it is normally not written. Okay, in every ionic bond or ionic compound, the valencies are attained by the crisscross method. Okay, let's move to the next one, which is magnesium oxide. Now, what is magnesium? Is willing to give away 2 electrons. Oxygen is willing to accept 2 electrons. Okay, I'll write it here. Magnesium ready to give away 2, so valency 2. Oxygen willing to accept 2, so valency 2. So here 2 and 2 cancel out. Okay, and that's the reason why both have a valency of 1 1, and that's how you write magnesium oxide. Aluminium oxide, I explained. Let me give you a few more examples on this. Let's take the example of magnesium iodide. Okay, magnesium is a group 2 element with how many protons? 12? Yes, protons 12. 12 protons. I am not writing the number of neutrons because not needed out here. Okay, so that means it has 2 electrons in the outermost shell. Iodine or iodide as an anion, belongs to group 7. That means it has 7 electrons. Okay, now when they have to bond, you know how they bond. Okay, but let me work on the valency. So magnesium and iodide. So magnesium has 2 as a valency. Yes, iodide has 1 as a valency. Going by the crisscross method, magnesium will have a charge of, or it will have 1. Okay, iodide will have 2. So magnesium iodide, the chemical formula for magnesium iodide will be MgI2. Understanding how the valency works in getting the chemical formula of an element, of a compound. Okay, potassium belongs to the group 2 element, that group 2 elements. Yeah, so it has 2 as a valency because it has 1 as a valency. Sorry, because it belongs to group 1 elements. Okay, so it has a valency of 1. Fluorine belongs to group 7. So to attain stability, it needs 1 more electron. So it has a valency of 1. Going by the crisscross method, both have 1 1. So the chemical formula of potassium fluoride is KF. Let's go to aluminium chloride. Aluminium symbol Al has a valency of 3. Chlorine belonging to the group 7 elements has a valency of 1. Going by the crisscross method, aluminium, since it's 1, we don't write it. Chlorine 3. So the chemical formula of aluminium chloride is AlCl3. Children, did you know that when you write a chemical formula, the metal is always written first, followed by the non-metal? Look here, potassium first, then fluoride. Magnesium first, then iodide. Aluminium first, and then chloride. So the metal comes first, followed by the non-metal. Okay, metal will always have a positive charge. The non-metal will always have a negative charge. Now, children, ionic bonds can have simple structures and joint structures. Okay, so sodium chloride is an ionic compound, we know that. Okay, it has the ion of sodium, which is Na. Since it's an ion, I have to write the charge, which is +1, and it has chlorine, which has a negative charge, which is Cl minus. It becomes chloride when we write it as an ion. They have equal and opposite electric charges, so they are strongly attracted to each other because they are equal and opposite. Understood this much? Okay, these forces, of electric charges is known as electrostatic force, which acts in all directions and forms of ionic bonds. So when there is an ionic bond of sodium chloride, okay, so if let me use colors over here. Okay, so if these are sodium atoms, okay, here, okay, they are sodium atoms, okay, all assuming that all are of the same size, okay, they bond with chloride ions, okay. Chloride basically is a little bigger than obviously it's bigger in size, okay. What's the number? 17, okay, bigger in size. So in from all directions, okay, in all directions, okay, these forces get attracted, or rather these forces attract each other, rather the forces of attraction are present. So there is a very systematic way in which these ions, the positive and negative ions, arrange each other. Okay, there's a very systematic way in which they arrange each other, and this systematic way of arrangement is called as the lattice. So they make them for it's a lattice arrangement. So then we say it's a lattice structure. Okay, so an example of giant ionic lattice is NaCl. Strong electrostatic forces exist between them simply because they are equal and opposite. Yes, then there is lattice energy because there is a pull from all directions. Yes, they have a high boiling and melting point. Yes, giant ionic structures like NaCl have a high boiling and melting point. Okay, they are hard and brittle, and yes, they are good conductors of electricity only when they are in molten form or in aqueous or dissolved form. Okay, because they are solids. Okay, in case they are solids, in case they turn into liquid, okay, then they can conduct electricity. Otherwise, they are poor conductors of electricity in the solid state. Okay, they are highly soluble and they are non-volatile. Children, what does volatile mean? Volatile means evaporates the liquid, mostly liquid or aqueous or dissolved form, evaporates at room temperature. So even if it is okay, these structures okay are in a molten form or in a dissolved form, they do not evaporate at room temperature, hence they are known as volatile, sorry, non-volatile. Okay, let's come to giant covalent structures. Okay, covalent structures where the electrons are shared. Children, many substances that have covalent bonds are formed of simple molecules And those simple molecules could be oxygen, carbon dioxide, methane. Okay, these are a few examples. This is because the forces holding the molecules together are very strong. I told you, when you share things, sharing is caring. Okay, the bonds are much stronger than that of ionic bonds. Okay, but the forces between the molecules are comparatively a little, sometimes a little weak as well. The forces between the molecules are known as intermolecular forces. We know that. Yes. Okay. So if I have water, okay, water bonds something like that, hydrogen bonded with two oxygen atoms. Okay. Then I have another water molecule. Okay. I may have another one. So these bondings are very, very strong. Amongst within each other is very bond. But this one to this one, the bonding is comparative is weak. Okay. So strong covalent bonds are very strong. Okay, but the bonding between the molecules is comparatively weak. Hope you understood that statement when I made that the covalent forces are bond, but the molecules are comparatively, they have weak intermolecular spaces. Okay. However, some covalent substances such as silicon dioxide, and diamond and graphite have giant covalent structures. Okay. Giant covalent structures have high melting and boiling points. Okay. They are hard. However, they are insoluble in water as well. Take some sulfur powder and try dissolving it into water. It will not get dissolved. Okay, it depends. Variable electrical conductivity, some are good, not some, but there are exceptions, but normally they are not good conductors of electricity. Okay. Then some examples of giant covalent bonds, as I stated, is diamond. Okay, graphite, silicon dioxide or silica. Okay, graphene, Buckminster fullerene, quite a few of them. Today we shall just look at maybe diamond and graphite. Okay, diamond and graphite are giant structures of carbon. We very often heard, and many a times it is a quiz question. Name the strongest material in nature. Okay, and we are like, it's diamond. Okay, diamond cannot be cut, it cannot be, diamond never breaks only because of its bonds. Okay, the bond, the covalent structure, the covalent bond that the carbon atoms make. Okay, this is so strong that that diamond can never ever break. Okay, so the carbon atoms in diamond form a real giant structure. Each carbon atom forms 4 strong covalent bonds. What do you understand by that? Okay, now see. We have, look at this one. Okay, look at this carbon atom. There is a bond with this one. This is the first one. It has a bond here with the second one. This one has a bond over here with the third one, and there will be one behind as well. Okay, look at this one. One over here, one over here, one over here, one over here. This one over here, one over here. Then there must be one behind. So each carbon atom has 4 strong covalent bonds. Why is diamond so strong? Why is it the hardest or the strongest material in nature? Because it has 4 strong covalent bonds. This is the only reason why it is the strongest material in nature or the hardest material on earth. It is not just used for jewelry, but it is also used for cutting and drilling tools. Did you know diamond is also used to cut glass? It is so hard because of the strong, rigid, three-dimensional structure of lattice. The arrangement of atoms, okay, makes it the strongest and the hardest material in nature. Understood, children? These large structures are called macromolecules. These are large structures, okay, and these large structures are called macromolecules. Okay. Now, there is another carbon, giant structure of carbon, which is exactly the opposite of diamond. That means diamond is the hardest material. Graphite, okay, another carbon structure, is a very soft material. Okay, graphite is, if you don't know what graphite is, it is the pencil lead, the lead which, when we uh, write or scrape it against a paper, it keeps losing out, and it's so soft that it comes off easily and puts a mark on the paper. Yes, so that's that. The graphite is basically your pencil lead. Okay, another use is it is used for lubricating moving parts in a machine. Okay, so graphite also has a lot of uses. In graphite, why is it the softest? Why is it so soft? Simply because it is missing out on the 4th bond. Every carbon atom does not make 4, but it makes 3 bonds. So if you take any of them, say if I take this one, so if I take this one, 1, 2, and there must be another one, 3 behind. Over here, this one, 1, 2, 3. This one, 1, 2, 3. So the softness of graphite is only because it does not have the 4th bond, and because of which, okay, it has only 3 bonds, and because of which it becomes a really strong, soft material, though being bond, though the main material is the main atom is carbon. Three three covalent bonds. What did I write here? 4 strong covalent bonds, three covalent bonds. Okay, just because the 4th bond is missing out, it is really soft. And moreover, graphite, apparently the arrangement is such that it is in layers. So when one layer gets scraped off, the new layer gets exposed. When the second layer gets scraped off, the third one gets exposed. So this is how it works best as a pencil lead as well. Okay, so basically in graphite, the carbon atoms each make bonds with 3 other atoms. Okay, and due to which layers are formed, which is very easy for them to slide over one another. Now, children, the carbon bonds between the carbon atoms in the layers are strong. Okay, in the layers they are strong, but the bonds between the layers, these bonds here, these bonds between the layers apparently is weak. So these are strong. These are strong. But just because they form these layers, this gets scraped off. This part will get scraped off easily. Then this part will get scraped off easily. Okay, and that's the reason why the bonds between the layers are weak, and so the layers slide over each other very easily. This makes the surface very very soft and and that's the reason why it easily comes off. This is what happens when you make a pencil mark on a paper. Understood, children? two of two carbon covalent bonds, one extremely hard and one soft, because just because of one missing bond or between the fourth carbon atom, due to which the layers are formed. All right, children. That's pretty much about properties of materials. Let's check our progress. The table shows some information about four elements. These elements are from the same group in the periodic table. They are given in the same order as in the periodic table. Okay, elements lithium, sodium, potassium, rubidium. Which group is it? It is from group 1. Melting points given 180, 63 and 39. Boiling point 1342, 883 and then 688. Reaction with water. Okay, when lithium reacts with water, it gives off bubbles of gases and gives off heat. Okay, sodium, maybe we have to find out. Okay, potassium, it gives off gas and gives off so much heat that it catches fire. Okay, and for rubidium, it explodes with such force that the container cracks. Okay, so rubidium is highly reactive, less reactive, potassium lesser reactive, sodium and the least reactive is lithium. Okay, there is a trend in the melting points and boiling points of these elements. Use a trend to predict the following. The melting point of sodium. Okay, where's sodium? The melting point of sodium. Here. So, would it be around? What would we predict? Could it be around anywhere between 100 and 120? I think we've done this. It was around 114 if I'm not mistaken. Can I write 114? Yes, pretty much yes. It's because it's a prediction. It has to be between these two. Correct? Okay, then. Okay, the boiling point of potassium. So, it has to be between 883 and 688. Okay, can I somewhere write 500? Simple assumptions may or may not be accurate, but it's just a prediction. The elements all react with water to produce a gas. Name the gas. We've done this last year, children, that whenever a metal comes in contact with water, it gives out hydrogen. Yes or no? And use the information about the reaction with water to predict the reaction between sodium and water. So what am I supposed to do? Use the information about the reaction with water to predict the reaction. Okay. So can I write it here? Sodium plus sodium, group 1 element, sodium plus water gives me sodium hydroxide and sodium hydroxide. It forms a base, remember children, NaOH, plus H2 gas is released. Yes, children? However, this equation is not balanced. Okay? Okay, hope this much is clear. Okay, the following, I'm doing the E1. The following are, so should I write it in small out here? Na plus H2O gives me NaOH, which is sodium hydroxide plus H2 gas. Okay. All right. Next one. The following are the mass of the four elements in the table above. Okay. Okay. Now match the numbers with the elements. Okay. So numbers with the elements. So 7 is for lithium. Okay, because third in the periodic table. Then this is 7. This is third in the periodic table. 11th, 19th, and this is how much? We'll predict whatever is left. Okay, so then 23, as in it'll be sodium. Okay, then potassium 19, so potassium, just K, and this is rubidium. Okay. All right. Match the numbers with the elements. Done. What does the mass number tell you about an atom of an element? That is, it is the total mass, which is the total number of protons plus neutrons in the nucleus. Lithium has 2 electron shells. The electronic structure is 2 and 1. Correct. So this can be seen in the diagram. Yes, it can. Okay, so sodium has the electronic configuration of 281. Draw a similar diagram to show the electronic structure of sodium. Children, we've practiced this. Yes or no? We have. Yes, so first shell has 2 electrons. Second will have 8. So done with 10, and this is how you will make your sodium atom. Okay. The fluorine atom has the electronic structure 2 and 7. This is shown in the diagram below. Draw a similar diagram to show the electronic structure of a fluorine ion. Okay, fluorine ion, that means you will simply have to make another structure like this, and you will have to add another electron out here to show stability, and you will write the letter F with a negative charge on top. Why is a fluorine ion more stable than a fluorine atom? Because its outermost shell becomes stable and full in capacity. Okay. Outermost shell becomes stable. Okay. Now the symbol for a fluorine atom is F. Write the symbol for a fluorine ion. Here, I've done it here. F with a minus, single minus. Okay, for each of the following, state whether this applies to a substance with covalent or ionic bond. Superb. When a metal joins with a non-metal to form a compound, it's an ionic bond. Okay, when two atoms share electrons, covalent bond. Children, we've done all this. when two non-metals join together. Non-metals join together, covalent bond. When a compound that is dissolved in water and conducts electricity. Tell me, children. So, this is a covalent bond. When a compound that is dissolved in water. Okay, and then the covalent bonds normally do not, when they're in the solid state, they do not conduct electricity, but in molten or aqueous form they do conduct electricity. Okay, when atoms gain or lose electrons, ionic bond. Okay, the diagram shows a molecule of methane. What is the formula for methane? Write the chemical formula for methane. 1 carbon atom and 4 hydrogen atoms. So it is CH4. The diagram shows the lattice structure of sodium chloride. Okay, what holds the lattice structure? Ionic bonds hold the lattice structure. Yes, what does this lattice structure tell you about the melting point and boiling point of sodium chloride? The melting point and boiling point of sodium chloride, children, it has a high melting and boiling point. Yes, this is what it states. Hope, children, the explanation was clear. The kind of questions that you may come across, how to answer them is clear. Okay, and I'm done with this chapter, children. If there's anything else that you want to know, please write it down for me in the comment section. That's all for today. Thank you and God bless you all.